Alright, so today I'm gonna be explaining another proof of equivalence of push-down automaton and context-free grammar. So a language is context-free if and only if some push-down automaton recognizes it. And when we say if and only if, it means context-free can lead to push-down automaton. It can be implemented or constructed by push-down automaton, and the reverse of that as well. For example, a push-down automaton, for any push-down automaton, there exists a context-free grammar. So we do the easier forward direction of proof, the easier, which is going from context-free grammar to a push-down automaton. So we want to construct a push-down automaton. So the push-down automaton begins by writing the start variable on its stack. First we have $sign in the stack, and then on top of that there is a start variable. Your start variable, for example, could be A, B, C, or could be 0 or 1. For example, if your alphabet is of the stack is 0 and 1, then your start could be any of that. And implementing this strategy requires an additional data. We need to see how the push-down automaton stores the intermediate strings as it goes from one to another. So let me tell you a beautiful example. I want to see, forget about this example. My tape is different. My input tape is, I want to see if it accepts, if this machine accepts my input string or not. So my input string, which is inside my language, has this form. I want to see if my machine accepts this or not. So first, we want to read the first one. So the first thing in the tape is here. And our stack at the beginning, as I said, at the beginning, we have $sign, we put $sign to see that there is nothing there. And then we start, our start symbol as, for example, I start with symbol 0, because I want to see if this string recognizes, and I know the start is 0. And then I know some rows. For example, I know only 2 rows. For example, A could be to go to 1. And this is a non-deterministic push-down automaton, so there is another rule. A could be A1. For example, if you have seen my playlist for context-free grammar, for example, you may write this as A goes to 1 or A goes to A1. So this is another way to summarize this. So we have only 2 rules, rule 1 and rule 2. And now I just replace 1 with A. I just replace 0 with A, and then so my stack becomes $, and then A. And then I replace A, so I use the rule number 2, and I replace A by A1. So $, and then A1 becomes like this. And now I want to use the rule 1. So I use rule 1, so instead of A, I use 1. So it becomes 1, 1. But here, if the top of the stack is a terminal symbol, such as A, my A is now 1, then you can read the next step. You read the next symbol. Now I can read the next symbol here, and it is 1, so it is okay. So I pop that and I go to the next one. So my stack looks like this: 1, 1, and then $. And then because the next one is 1, so it's okay, it accepts, they match here. So because they match, I can pop that and look at the next one. So my stack is now updated like this, dollar and then 1. So I read the next one, I see the next one is 1 and say, okay, because they match together, I can pop that, and finally I reach this dollar and everything is empty. So I started from height 0 of my stack. So this is the height, for example, of my stack. And I increase that and then increase the height of the stack. And then I decrease that and then I decrease that until it reaches the beginning. So until it reaches the 0. I start from here and then I reached here. So it was like the trajectory of the height of the stack was like this. It was increased like this, and then decreased. So this is the graph of that. This is very important because I want to show you that you can work on this and look at this like this. For example, if you want to go from state P to state Q, you should first go to state R, and then you go from state R to state Q. The reason is that we can associate a grammar rule, a rule like this, that's saying that from going from state P to Q, first we go from P to R and then to RQ. But the trick that we use is that the height of our stack does not change. So it can go many trajectories. This one goes down and reaches here. Or if we want to pass the state R, it should go up and then reaches the state R and again going up. But the height of the stack should come back to the original level. And we use this in the proof of the theorem. So now you know everything about this example. And so we are in state Q, and our input tape is A, and the stack is S, because as I said, we have dollar, and then the beginning start symbol is S, which for our case was 1. And then we continue. We go to state Q1. And from Q1, we go to state Q2. From Q2, we go to state Q3. And, these are the things that comes to the top of the stack. And so going from state Q to state R involves some intermediate states, such as Q1 and Q2, which I explained. And now there are 3 cases in our algorithm: case A, case B, case C. In case A, if the top of the stack is A, you just use one of these rules that you know, this one or this one. But if the top of the stack is a terminal, as I said, for example, if it is 1, we see if they match, we repeat it. If they do not match, we reject it, because we say that that string is not accepted by our machine. You should either change your rules, you should update, you should develop your grammar rules, or you say, if you want to be dogmatic and say, no, I don't want to change my idea, then you say that this is not rejected. This is rejected by our machine, and because we don't want to change the set of our rules in our grammar. And now we are here. So for case A, as I said, the top of the stack is just a symbol, so we just use one of our rules. For case B, that our top of the stack is a symbol like 1, or terminal is a terminal like 0 or 1. So for that case, we just check if it matches, we read the next one. If it doesn't match, then we reject it immediately, and we don't even look at the future steps. And finally, you know that you are at the end of that, and you come back to the original stack, empty stack marker on top of your stack. And so the trajectory is something like this. You go up, you go down. but the height of the stack remains the same. You may either go different trajectories, but this is important that you come back to the original height of the stack. And so this is an example. The transition function is shown. We have two rows. And so here, this is OR. For example, it says S goes to ATB, or you can use another rule, S goes immediately to B. And because we have different rules, you have different, so non-determinism comes from these things, because you have different rules, different combinatorial things may happen. Different combinations can happen, and that's why it is non-deterministic. And it can go and reaches different trajectory. This is one trajectory, this is another trajectory, this is another trajectory, and they are very complex. Especially if the number of your alphabets are increasing, it becomes very, very complex and interesting. So we prove we have a push-down automaton P. We want to make a context-free grammar that generates all strings that P accepts. In other words, G should generate a string if that string causes the push-down automaton to go from its start state to an accept state. To achieve this outcome, we design a grammar that does somewhat more. For each pair of states P and Q in your push-down automaton, the grammar will have a variable APQ. So we simplify our task by modifying our push-down automaton to give it the following three features. First, it has a single accept state, because if you don't reach an accept state, you don't know how much you should go. Your tape, you don't know when you should accept it. And it empties this stack before accepting, and each transition either pushes a symbol onto a stack or pops off the stack. But for simplicity, we assume it does not do both at the same time. So, for example, this is another rule. A is the input at the first move, B is the input read at the last move, and there are some intermediate things that we go from R to S. So finally, you either go from P to R, R to Q, or you say you have so you have two things. You have either go like this, or going from you have three things. Your rule is composed of three things. One terminal A, this is terminal, this is non-terminal RS, and then finally B. And that's it.